Good afternoon, everyone. So my name's Liron. I lead up business development at Starknet. I've been there for 3 years. I'm here because of the nature of the conference. I'm assuming some sort of prerequisite knowledge with just the L2 space, blockchain in general. And I thought it would be nice to do a bit of a deep dive in a technical breakthrough coming on our end, which will significantly reduce gas costs and also help with scalability. I will stay after the talk in the foyer to chat other stuff, maybe the less technical, more biz dev stuff. So that's it from me. Let's get straight into it. So Starknet, who we are one of the leading teams building validity rollups on Ethereum. The Stark technology was invented by one of our co-founding team, Michael Ryabzev and Eli Ben-Sasson, and 2 others. You're probably familiar with StarkX, our SaaS product that powers DYDX, Immutable, Sorare, a bunch of other teams. Starknet is our permissionless blockchain. They all use this shared prover called Sharp, Sharp being shared prover, which I'll do a bit of a deep dive in. And we have the current prover that Sharp uses is a stone, like prover number 1, and there's a prover number 2 called Stu, which will be coming out hopefully into production in Q1 next year. That's a bit of an overview of metrics just to set the table. Over $1 trillion of trading volume settled by us. TVL of over $2 billion, and over 800 million transactions processed through our systems, whether it's the StarkX systems or public Starknet. Completely transitioning now to the more technical stuff. So let's go through the life cycle of a Starknet block as it is today. So you are a user on Starknet, you have your wallet, you go to your favorite app, you submit transactions. They are in this centralized mempool that we run, and we put them through the sequencer. The sequencer then forms blocks, and each of those blocks gets sent as a job to the shared prover. Perhaps a sentence about the shared prover. So the magic of Stark proofs is that the verification is logarithmic to the size of the computation. So it's roughly 9 million gas to verify a proof on Ethereum, pretty much regardless of the size of the proof. There's some overhead, and then assuming the proof is sufficiently big, it's roughly 9 million gas regardless of how many transactions are going through. So because of that, we want to put as many transactions as possible. So we do this recursive proving off-chain. And then we do these proofs of proofs of proofs of proofs. Like imagine it's like binary tree, boom, 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 into a single proof that then gets sent to Ethereum. And that's happening through what's called the shared prover. The shared prover is receiving jobs from Starknet, from StarkX, from random different teams who want to send different Cairo jobs. And they all get sent through Sharp. So even today, each Starknet block itself is one of these jobs that the shared prover receives. And then they get settled to Ethereum. There are always 2 components to what's sent to Ethereum. One is the actual proof, and the other one is the data availability. The analogy I like to use with this is I can prove to you that X equals X, but you don't know what X is. So separate to the actual verification of computation that happens at the top, we also have data availability getting sent through on the bottom. The recursive tree I was describing before, this binary tree that we have for generating proofs, this is how it looks today. You have each leaf of the tree is a Starknet block. Each of those blocks gets independently proven. And then you recursively prove a verification of the concatenation of 2 of those proofs. So if you look at this in the top right, you've got proof 1, 2. What that means is it's a proof of the verification of proof 1 and proof 2, until you eventually get to a root verification that is then sent to Ethereum to be proved. The magic about this is that, oversimplifying things, the gas costs to verify on Ethereum are roughly fixed, regardless of the size of the computation. So by having this whole tree condensed into one root of that tree. Ethereum is giving you security to the entire tree for roughly the same cost as if you would have just sent one of those jobs directly to Ethereum. That is sharp today with Starknet. Again, the leaves in this example are different Starknet blocks, but in production today, it's not just Starknet blocks. Sorry. It's also different instances of our StarkX products and just general computation the teams want to improve. What are the issues with this? Yeah, as described. Okay, so one issue with this is, remember I said there are two components that are being sent to Ethereum. One is the proof that's being verified, and another is actual like data availability about that proof. So with this data availability, every single block that we send currently is registering its own facts on Ethereum, which, to simplify what that means, is every single block today in production has its own gas footprint on Ethereum, which is something we want to avoid. One of the whole benefits of the ZK rollup space is that you're not meant to grow linearly with the size of the computation when sending to Ethereum. You should be growing logarithmically, and that's why we need them more than we need optimistic rollups in the long term. Again, in the long term. So yeah, every single block is proven through Sharp, and also every has its own fact that is registered. What this now means in today's architecture, what I've just been describing, the gas footprint, you have 86,000 gas per block in terms of gas footprint on L1. And then you also have these blobs, which have the data availability that have their own gas footprint as well. 50,000 gas, there's 23,000 gas for fact registration, 36,000 gas for memory, et cetera, et cetera, et cetera. The point is, bottom line, take one thing out of that side, you've got 200,000 gas fixed costs for every single block, every single Starknet block that's being proven, even though you have the shared prover, which is being done recursively. This is really limiting, because if you have 200,000 gas per block, and you want to eventually have 2-second blocks, even 12-second blocks, you automatically, 12-second blocks, you have 1 million gas being spent per minute just in the overhead per block before you even get to the actual marginal stuff with the verification. Super not scalable, and we're stuck. We're sort of back to square one with blockchain scalability. So we want to sort of avoid this issue of having a fixed gas footprint per block in order to help these validity roll-up scaling. I'm seeing some faces that are understanding this, just trying to assess my audience, which is good. So I'm going to continue at this pace. If you have questions, you can raise your hand. Yeah, this sucks because it's linear in the number of blocks, which is frustrating. And it's something that we can avoid. So we want to avoid that. That's what we're releasing. That's the whole punchline of this talk. How do we so a few efforts we've been doing to reduce the L1 costs. One thing is that every Starknet block, if we're anyways paying this 200,000 gas per block, well, let's at least make the block as big as possible. So we've gone from 10 million Cairo steps, which is our unit of gas, to 45 million Cairo steps per block. Another change, yeah, so that's great because you can write less facts per unit of computation, less frequent state updates. You're anyways, there's a lot of blob space that is able to be used. The problem is, yeah, bigger machines are required to prove because you're proving, proving is super linear, n log n. So you pay on that side, and it takes a bit more time and a longer finality because there's bigger block sizes. And it's also still linear in the number of blocks, which hasn't solved the initial problem that I was describing. But we have a solution for this. So it's called block packing. If you've been following us closely, you might have seen this as applicative recursion. I pushed very hard to rename that because applicative recursion is not a good name. It doesn't. What's really happening is block packing. So let's describe what's going on. This we already went through earlier. So currently you have these transactions that get sent to the sequencer. The sequencer forms blocks. The blocks are sent to Sharp. Each block has its own Sharp job. But now with block packing, what you can do is, if we like double click or magnify on that proving tree that we saw before, take one of those leaves out. I don't have a laser, but you see that proof ABCD? Let's expand that. That itself, even though there's one leaf in like the Sharp tree, that itself consists of its own tree of recursively proved jobs, which are squashed into proof ABCD. Now, it's different to the, it's like a leaf in the recursive tree of Sharp itself consists of a bunch of recursively proved stuff. The advantage being that all of the state updates going through job A, job B, job C, and job D are squashed into one state difference. That is then only that state difference going from A to D has a gas footprint on L1. I want to explain what this means. Let's say you have Alice and Bob. And Alice in block A sends Bob 1,000,000 ETH. And then in block B, Bob sends that 1,000,000 ETH back to Alice. And then in block C, Alice sends it back to Bob. And in block D, Bob sends it back to Alice. So in the naive approach that we've had in production today, you have 4 state updates sent onto L1, each of those telling you who sent the ETH each time. Today, with what that describes, with what that describes, you condense that all into one state update, and that state update is 0 because we just sent money back and forth. And after the 4th block, we both ended with what we started. So you now have no gas footprint to represent those state updates because they're all condensed into one leaf, which has no net state update. Yeah, and then what do we have? We have the facts and we have the proof, but as I just described, in that example, the facts are condensed, aggregated into one state diff from all of those different blocks, which now has a lower gas footprint. So we finally decoupled the number of blocks with the gas footprint. And if you've completely spaced out, this is the one line to take from this talk, is that this architecture allows you to now decouple gas footprint on L1 and the number of blocks you have on L2, which to today, we were paying 200,000 gas per block on L1, just table stakes, just to get it going. Now we've decoupled that. There's no fixed cost per block. Great. So yeah, L1 cost today, you have this state update, you pay per block. KZG pre-comp, you pay per blob. Fact registry, memory page, all those per block. Sucks, because it's all per block and per blob. Now you move, instead of paying per block, all of those things, you're paying them per block packing tree. And then you have the scalability, and now today, for example, production, blocks are coming like every 6 minutes, let's say, because we're sort of waiting for them to fill up in order to send them to Ethereum, because we don't want to pay that we don't want the users really to pay 200,000 gas per block. Now we don't have to wait 6 minutes. We can have a fixed block time of a few seconds, and we're not worried about having an exorbitant L1 footprint. Decouples the Starknet block frequency from the L1 costs. Also have full blob utilization because you can make sure that the blob is covering more blocks, and then still divide that across all the transactions in all of those blocks. And most importantly, reducing your L1 costs per transaction, which is just a fantastic win for everybody. I look back at, I speak at this conference like every year, and I look back at the past 12 months, and one thing that's really changed is the gas costs for like individual transactions are no longer a blocker for the individual user. And it's not just because demand is down. demand is down, but it's separate to that. With 4844, with L2 scaling, with blobs, with decoupling the number of blocks and the gas footprint, you have this like world where the average transaction is sub 5 cents. Vitalik put that as like I think it makes sense, like a reasonable like upper limit per block. And you're seeing this reduction, and it's going to scale as well, which is the big thing. Thank you. Cool. Any questions or comments? Great. Just repeat the question for the...
Yeah, and so how often do you plan to save such a checkpoint, such proofs to the layer 1 chain? Every 10 block, 100 blocks, or how often?
That's a good question. Yes, he's asking how often do we plan to send those blocks to be proved on L1. Currently, we do it every like 6 hours, which is way too like long to wait. What the long-term goal is a good question. I'm cautious to say. Basically, it becomes a question of how much we're willing to pay for that. Even if it's every 10 to 20 blocks, it probably becomes too expensive if it's 6 million gas or 6 to 10 million gas to verify a proof. But if those recursive proofs don't just have those 10 to 20 blocks from L2, but also these different app chains, then it could be affordable. But to answer your question in a different way, what becomes the limiting factor is the actual financial cost of verifying a proof. It is not, and this is also something I've changed in the past 12 months, it is not a latency question in terms of proof generation. Like that, especially with these recursive proofs, you can actually prove a lot of stuff in parallel and reduce the proving time to minutes. It becomes an economic question of how much do you want to be paying the L1 costs.
Thank you.
I got a question too. When A, B, C, and D all net to 0 and there's no state difference, are A, B, C, and D still verifiable on the L1 even though you don't commit any gas?
Yes. Okay, this is a good question, and it's something I think a lot of people don't understand. What's sent to L1 is not, you don't have a representation of each individual transaction on L1 today. And that will never happen. That's by design. Unlike the optimistic rollups, I'm not here to trash them, they're great, they're important. But because of the nature of fraud proofs, they have to have a representation of each individual transaction on L1. With us, with validity rollups, you're proving that the transition from the state before that block to the state after that block, let's be more generalist. The previous state to the current state is valid. But all you care about is what changed between those two states. So you can prove that nothing changed even though we went back and forth 4 times. So in that example of going back and forth, sending the money back and forth and ending up net the same, you're still proving that given all of these 4 transactions, nothing changed. And therefore, Ethereum knows nothing changed, but it also knows that those transactions, that a bunch of transactions happened. Please.
Thank you. So in your presentation, and even now, you gave an example that what happens is that Alice transfers funds to Bob, and Bob back to Alice, and then it all cancels out, and you have a smaller state diff. But what happens if things don't cancel out, when you have a larger state diff? And then I don't understand, what's the difference between this and just creating a very large block? Does it?
Good question. So you won't, if you have all these transactions that touch different storage slots and they don't cancel out, you have no benefits from this. But you're not worse off than doing this. So you're right, in that situation, things will not improve. You have to remember though that at least in the current applications that run on blockchains, majority of transactions do touch the same slots. So if you think about Ethereum, most is minting and redemption of stablecoins by large institutions with the same wallets. Uniswap traders, most of the trades are done by a minority of wallets. So you do see benefits in production, in the real world, at least in the current state of things, from doing this thing because the state diffs are often occupied by the same storage slots.
Thank you. And if I can have another question, was recursive proofs, they work like Plonky, what Polygon did, or is it like something new? I'm just...
We use Stark, not Plunky 2 or Graph 16 or anything like that. Are you talking about like the actual like...
Like the recursive method which you're using. I just know of Plonky and I don't know about any other method. I was wondering if you guys invented something new because I'm kind of out of touch lately.
So we use Starks, like that's the whole unique thing here.
Yeah, but it's like recursive Stark, so you need to have like a special method. Never mind.
Yeah, so we can talk about it in the foyer or something.
Never mind.
But the point
offline.
is that each leaf is proven with the same prover that we use for the final leaf. It's not we use the same prover for every stage of the
just Starks for actually it is possible. Okay, I think I understand. Sorry.
Thank you, everyone.